people. Very nice to come to Hsinchu for the second time this year. Anyway, so today I'm going to talk about the prospects of searching for dark photons at the future, proposed future colliders called the LHeC and FCC-he. This is one of my recent works in collaboration with Monica and Oliver. As you all know, there's abundant evidence for the existence of dark matter, for example, galaxy rotation curves, structure formation, etc. So, in order to explain such dark matter, one of the possibilities is a class of hidden sector theories, which usually predict new particles to interact with standard model particle via feebly coupled mediated particles. Namely, there can be different portals, so-called portals, to connect the dark sector and the standard model. So in this talk, we just focus on the vector portal, and the corresponding mediator is the dark photon. Such physics scenario has been studied at various environments, colliders, spin down, fixed time experiments, etc. In this talk, so I will show that if we make use of electron-proton colliders, the sensitivity reach may be unique, and we focus on LHeC and FCC-he. So, brief introduction to the model, dark photon model, where basically we just extend the standard model gauge group by an additional broken gauge group, U1x, leading to this retina here, usually known as kinetic mixing. If we apply field recognition to get rid of it, we can basically come to this term, where we see the dark photon is coupled to a pair of standard model fermions with a coupling epsilon times E times the charge of the fermions. So it's like an analog of the standard model photon, but coupling is suppressed by a small factor epsilon. So dark photon mass. So dark photon can be massive, and the mass can stem from, for example, a Higgs mechanism. And in this model, because we just assume standard model particles are uncharged under this new U1x. And we end up with two parameters, dark photon mass and mixing epsilon. In fact, the latter, the epsilon, actually controls both the production and decay of dark photons. And we focus on MeV to GeV mass range in this work. The only possible non-gravitational portals connecting the standard model sector and the dark sector are listed here. You have scalar, pseudo-scalar, vector, and neutrino portals, corresponding respectively to the second Higgs or Higgs-like particles, dark photons, and heavy neutral leptons as the mediator. We focus on dark photons, which could be the messenger to the dark sector, or even constitute dark matter itself, motivating such searches. Here is a brief introduction to the collider environment. So as I said, LHeC and FCC-he are proposed future detectors. Both of them make use of electron beam of 60 GeV, while the energy of the proton beams are different, 7 and 50 TeV. And leading to a different center mass energy at 1.3 and 3.5 TeV. And here we also show the expected, projected final integrated luminosity. So the physics process is like you have a proton and electron, they collide each other. So at the primary vertex, you have an electron, dark photon, and some other hadron coming out, and the dark photon becomes a bit displaced and decay to a pair of charged particles. In this talk, we focus on the deep inelastic scattering regime. That is, the transfer momentum squared is much larger than proton mass squared. And in such regime, the most dark photons would come off the electron beams. So how to estimate the number of signals? Since this is a displaced search, we have the number of displaced vertices equals to the production cross-section, the scattering cross-section, times L is the integrated luminosity, and then times the integral of the, so D is the density function of the dark photons with a certain polar angle and boost factor, and P here is just decay exponential probability function, making use of the detector geometries and the boosted decay length, where for the minimal distance x, we take 200 micrometer because usually in the relevant parameter space, in this work in the relevant parameter space, our dark photons usually decay before they reach the beam pipe. Oh, sorry, I'm confused. 200 micrometer is because we have for the gliders the spatial tracking resolution, and the x max is taken to be infinity because most of dark photons decay before they reach the beam pipe, and delta x lab is just boosted decaying in the lab frame. And here I also showed the acceptance of LHeC and FCC-he for the final state electron, muon, jets. And in practice, we just applied absolute value of pseudo rapidity less than 4.7. And here is just a plot for the distribution of dark photons for their pseudo rapidity and the momentum. We noticed for 3 dark photon masses, 100, 300, 500 MeV, I've noticed that most of dark photons have small momentum and peak at certain pseudo rapidity. We also need to know how to describe the dark photon decay. So from this plot, from this reference, we see that in the relevant mass range, dark photon, so from 0.1 to 1.0 GeV, dark photon may decay to lepton pairs or some hadrons, in this case, maybe pion pairs. And what we do is just we analytically calculate the partial decay width of dark photon into a pair of muon or electron with this formula, and then if you extract the branching ratio from this plot, you can describe the total decay width.
I'm sorry. Can dark photon decay to W plus?
Well, then this must, you mean W? Boson?
Yeah, so W plus W minus.
Yeah, that must be offshore, right?
Well, the mass is heavy enough.
But here it's only 2, 3, right? So here I just talk briefly about the background as well. 2 kinds of sources. One is real low energy photons coming from the same process. They may interact the detector material or beam pipe, leading to photon conversion process. So we see electron-positron pairs. But in principle, the location of the secondary vertices then would coincide with the detector material or beam pipe. So they can be easily identified. And we can also have long-lived hadrons, such as K short, K long, and lambda baryon. Their lifetimes are much larger than the distance from the. Their lifetime is quite large from the IP, and more importantly, maybe the hadronic activity is usually aligned with the proton beam and propagates mostly into the forward hemisphere of the detector, while our dark photon mostly come off the electron beam, so it's in the other hemisphere of the detector. And also such hadrons, their primary decay channels are only marginally consistent with our signal signature. Plus their masses are well known, so just we argue that they can be easily identified or rejected. So here I show you some plots for the results. So in these plots, we assume 0 background, and 100% signal efficiency, and the upper row is for LHeC and the lower row is for FCC-he. On the left-hand side, on the left column, we apply a PT cut on the final state hadron at 5 GeV. And on the right, it's 10 GeV. So ensure that we are working on a deep inelastic scattering regime. So we show 3 lines, blue, red, and black, corresponding to 1, 10, and 100 signal events. So, well, if you look at the 10 signal events curves, roughly our these two colliders can be sensitive roughly around 0.4 GeV dark photon mass at 10 to minus 4 for epsilon. Of course, we may have reduced the sensitivity if we have more background events or if we have less signal efficiencies. So here are the 2 plots for LHeC and FCC-he respectively, both of which for PT cut at 5 GeV. So the red curves are for 0 background events, and the red curves are for 100 background events, while the solid lines are for full 100% signal efficiency, and the dashed lines are for 20% signal efficiencies. And the dark gray area are the present exclusion region, and this light gray area is roughly the currently sensitive area from the LHCb experiment. So even for the worst case, we can cover regions beyond the present exclusion limit. Finally, we compare our results with all the other experiments. Here's a plot extracted from the recent physics European Strategy for Particle Physics briefing book work. So here the red curves are for FCC-he and LHeC, and here's the inclusion of all the other experiments, colliders, B factories, beam dump experiment, etc. So these curves correspond to 10 signal events, 0 background with 100 efficiency for PT cut at 5 GeV. So very clearly, we see that our results at the electron-proton colliders can be unique, probing this part of area. So here I would like to summarize my talk. Dark matter may reside in a dark sector connected to the standard model by different portals. In this talk, we focus on the vector portal concerning a dark photon, which may provide this connection or constitute the dark matter itself. And there are lots of new and existing searches going on, hunting for such dark photons. We show that the unique environment of electron-proton colliders may explore then a difficult territory in the parameter space for these sub-GeV dark photons. Thank you.
Some time for questions. Okay. And any reason why the LHeC cannot probe heavier than larger than 1 GeV dark photon? And the reason why in your plot you only show up to maybe 0.6, 0.7 GeV.
Yes.
Heavier than this factor. I mean, maybe not this factor, but here is one, the coupling. There's something like that here. You only couple to about 0.8 GeV. Any reason why it doesn't go beyond that, like a few GeV? Certainly, according to that graph, maybe the event rate are much 110 1 maybe 0.1. And NDP to mine is
It's
getting
heavier than it decay faster.
decay faster.
You won't see a displacement effects.
Oh, okay.
It's
But as long as your couplings epsilon is getting smaller.
but
It's
then
small.
you don't get enough
Okay,
signal
I see.
events.
Okay.
Because epsilon controls both production.
How to estimate the background of the displaced vertex?
No big.
Here we argue that there's no background. In principle, if you want to do a detailed study, you need to do simulation. You
Yeah.
generate those chaos, for example, then you check their decay position.
So if there's no background, how do you calculate, for example, significance?
No, usually they take 3 events.
Oh,
If
they
there's
take
no
it
background,
randomly.
3 events is 95 confidence level of sensitivity.
Other questions? Okay.